Right. So in this video, we will solve the differential equation 5 plus x squared y prime plus 7xy equals to 0 using a power series about x equals to 0. So we're going to assume a series of the form y equals to sigma n equals 0 to infinity of c sub n x to the n, whose derivative is y prime equals to n sigma n equals 1 to infinity of n c sub n x to the n minus 1. And we need to take the first derivative again because the differential equation calls for that first derivative. So before substituting the series and its derivative, it would be a good idea if we distribute the y prime over the sum of these two terms inside in the differential equation, so inside of the parentheses. That's going to leave us with 5y prime plus um, x squared y prime plus 7x y equals to 0, right? Now, substituting the series into the differential equation, that should lead us with the following. That is 5 sigma n equals 0 to n equals 1 to infinity of n c sub n x to the n minus 1 plus x squared sigma n equals 1 to infinity of n c sub n x to the n minus 1 plus 7x sigma n equals 0 to infinity of c sub n x to the n, and let that be equal to 0. All right? So, before combining the series into a single one, there's a couple of operations that we need to do. Introduce the 5 in the first series, the x word in the second, and the 7x in the third one. That's going to leave us with sigma n equals 1 to infinity of 5n c sub n x to the n minus 1 plus sigma n equals 1 to infinity of n c sub n x to the n plus 1, because x to the n minus 1 times x squared at the exponents, that's going to leave us with n plus 1. And then plus sigma n equals 0 to infinity of 7 c sub n x to the another n plus 1, because x to the n times x to the first, that's x to the n plus 1. And let that be equal to 0. All right. So the next step is to find a way to write all series having the same starting index and the same power of x. And typically what we do is write all series in terms of the starting index n equals to 0. That's not always the case, right? But in this case, it will be. But we're going to look at the highest power of x in this case, which is n plus 1. All right, so notice the second and the third series have the power n plus 1. However, the second series starts at n equals to 1. Well, here we need to decide whether to do some shifting and what kind of shifting. Well, if we do a complete shifting, that actually messes is going to mess up the power of n. However, because of this factor n, we can simply do an incomplete shifting, because if we start the same series at n equals to 0, that's not going to affect, because n equals 0 is 0 times c sub 0, x to the 0 plus 1, everything is going to be equal to 0. So it's not going to affect whether we start the 0 at n equals to 1 or at n equals to 0. All right. However, for the first series, well, notice how we have the power x to the n minus 1 versus power n plus 1. In this case, n minus 1 and n plus 1 differ by 2 units. So if we're thinking of adding 2 units to all n's in the series, that'll imply subtract 2 units to the starting index, and then but that's going to be a problem. Although on the one hand it's going to fix the power of x to have all the same, that's going to leave us with a weird starting index that is a -1. And again, that's taking us to the dark side of the series, right? We don't want to have negative starting indices because it's not a power series. So to prevent us from um, going to that dark side of the series, well, in this case, we're going to expand the term corresponding to n equals to 1, and you'll see what's going to happen. right? So that'll be 5 times 1 times c sub 1, okay? X to the 1 minus 1. It's a little too high, okay? And well, that's now that we expanded the term corresponding to n equals to 1, the series now starts at n equal to 2. All right. Now, starting our series at n equals to 2, will if we perform a complete shifting, adding 2 units to the exponent and the subscript and the factor n, subtracting the 2 units in the starting index, that's actually going to fix everything, and we will be able to combine all in one single series. All right. So the second series in complete shifting, that is plus sigma n equals 0 to infinity, and c sub n x to the n plus 1 plus 7, oh wait, sigma n equals 0 to infinity of 7 c sub n x to the n plus 1. And that equals to 0. All right. Well, let's simplify what we have so far. So 5 times 1 equals to 5. C1, x to the 1 minus 1, that's x to the 0, which is 1. 1 times c sub 1 times 5, that's simply 5 times c1. All right. And then at this point, I'm going to do the complete shifting to the first series. So plus 2 to all ends in the series, and minus 2 at the starting index. Okay. So this will be plus sigma n equals 0 to infinity of 5 times n plus 2 times c sub n plus 2 x to the n plus 1 plus sigma n equals 0 to infinity of n c sub n x to the n plus 1 plus sigma n equals 0 to infinity of 7 c sub n x to the n plus 1. And let that be equal to 0. All right, so notice how now all of these series have the same starting index and the same powers of x. That means they are all like series. All right, so we should be able to combine them into a single one at this point. So this will be 5c1. I'm going to factor the sigma symbol on the left from bracket, 5 times n plus 2, c sub n plus 2, plus n c sub n plus 7 c sub n. And I'm going to factor the x to the n plus 1 on the right. All right. And at this point, we're ready to equate coefficients, write our recurrence relation, and all of that. All right. So uh, the fact, okay, so this constant on the left hand side equals to the constant on the right, that is 5c1 equals to 0, which means c1 equals to 0. And then the power or the coefficient of x to the n plus 1 on the left-hand side must be equal to the coefficient of x to the n plus 1, but we don't see anything on the right-hand side. Well, that means it's equal to 0. So that is 5 times n plus 2 times c sub n plus 2 plus n c sub n plus 7 c sub n. Let that be equal to 0. All right. Now we would need to solve this equation for the C containing the largest substrate, in this case, C sub n plus 2. This in order to obtain our recurrence relation. However, before solving, I'd rather factor C sub n from the second and the third term. That is plus n plus 7 times C sub n equal to 0, in addition to 5 times n plus 2 c sub n plus 2. All right, so at this point, we may solve for c sub n plus 2. Okay, so I'm going to subtract n plus 7 c sub n on both sides and then divide both sides by 5n times n plus 2. So that's going to leave us with c sub n plus 2 equals to negative n plus 7 c sub n divided by 5 times n plus 2. All right, so that's going to be our recurrence relation. All right, guys. Well, we have what we're going to notice with this recurrence relation is that each coefficient here will only depend on two indices. That's because n plus 2, between n plus 2, the subscript, and n in the on the right hand side, these two differ by 2 units. All right. So that means the coefficients will split into two independent chains. What are those chains? So number one, a change for c sub 0 and a change for c sub 1, right? So for c sub 0, that's actually, if we continue the pattern, that's going to be a c sub 2, c sub 4, c sub 6, etc. Starting at C sub 1, adding 2 units because they differ by 2 units. The next one would be C sub 3, C sub 5, C sub 7, etc. So, why is important to do this? Because you don't want to compute too many coefficients, so in order to be able to see the pattern. Instead, um, see how the coefficients split into two chains or three chains or four chains, depending on how many units do the subscript differ for the c's. Because also, what do we know about c sub 1? C sub 1 equals to 0. So because in this case, c sub 1 equals to 0, that means the entire chain of coefficients is going to be equal to 0. So all you need is to compute the coefficients corresponding for c sub 0, c sub 2, c sub 4, c sub 6, etc. Actually, again, we don't need to compute that many anyway. So here we go. Let's compute the coefficient for n equals to 0, all right? So that is, so for n equals to 0, that is c sub 0 plus 2, that equals to 2, equals to negative 0 plus 7, that is 7 c sub 0, divided by 5 times 0 plus 2, which is 2. So that's our coefficient of x squared, right? And then, well, n equals to, what's the next one? N equals to 2, that is c sub 2 plus 2, is that equal to c sub 4, equals to negative 2 plus 7, which is 9, times c sub 2, okay? And then divide that by 5 times 2 plus 2, which equals to 4. But you might want to write c sub 2 in terms of c sub 0. So in this case, that'll be negative 9 over 5 times 4 times c sub 2, which is negative 7 over 5 times 2. And that times c sub 0. All right? So that'll be negative times a negative equals to positive 9 times 7 divided by 5 times 5. Again, do not cancel any coefficients. So my advice here for this kind of exercise, I'm gonna write this 5 times 5 as a 5 squared, not as a 25, as a 5 squared. Because we might want to see a pattern with powers and all of that. And that times 4 times 2. Okay? And that times c sub 0. And for n equals to 4, rather, not 3, 4. For n equals to 4, so that'll be c sub 4 plus 2, is that equal to c sub 6, which is equal to negative 4 plus 7, that is 11 times c sub 4, and divide everything by 5 times 4 plus 2, which is 6. But again, you might want to write c sub 0 in terms of c sub 4 in terms of c sub 0, but we have that from the previous calculation. That is negative 11 over 5 times 6 times 9 times 7 divided by 5 squared times 4 times 2, c sub 0, which is equal to 11 times 9 times 7 divided by 5 cubed in this case, because it's 5 times 5 squared, that's 5 cubed, all right? And 6 times 4 times 2 times 6 times 4 times 2, all right? Okay, so it seems like this is more than good enough to the generation of the coefficient. We add another page in here, okay? So We're going to write our solution as a power series. That's going to be y equals to, remember, I'm not going to write the entire polynomial. Remember, C1, C3, C5, C7, all of those coefficients were 0. Well, so that means I'm going to write C sub 0 plus C2 x squared plus C4 x to the fourth plus C6 x to the sixth plus etc. infinitely many terms. All right. Well, so let's start by writing the c sub 0. So y equals to c sub 0 is simply c sub 0. That's our arbitrary constant, if you will. Okay, make it look like a 0. And that's going to be negative 7 over 5 times 2 minus 7 over 5 times 2 c sub 0 x squared plus c sub 4. C sub 4, which is 9 times 7 over 5 squared times 4 times 2. C sub 0 x to the fourth minus, all right, so, oh, I forgot a minus over here. Again, I believe I did that in the other video. Okay, so that's minus 11 times 9 times 7 over 5 cubed times 6 times 4 times 2. C sub 0 x to the 6th power. Why is that? Because here, this coefficient, because of the subscript 2, that corresponds to the coefficient of x squared, the coefficient of x to the 4, the coefficient of x to the 6. All right? Well, so the next part is to, next step rather, is to find a pattern and write this as a power series. Well, let me first of all factor c sub 0. So that's y um, y equals to c sub 0 times 1 minus 7 over 2, or 5 times 2, x squared plus 9 over 9 times 7 over 5 squared times 4 times 2, x to the fourth minus 11 times 9 times 7 over 5 cubed times 6 times 4 times 2, x to the 6, and then plus infinitely many terms. Okay? And from here, we're going to write this using sigma notation. And the way we're going to write the series is going to be very similar to what we did in the previous example. I'm gonna look for a pattern for the terms containing powers 2, 4, 6, and on, and I'm gonna leave the 1 by itself, right? Because of this increasing product, that's not going to be a good idea to. It's not. It's going to be a weird behavior with that increasing product. Anyway, so let's see what about it. Actually, let me write that 6, 4, and 2. So in this case, see how that 6, 4, 2 is pretty similar to that power 6. But also, actually, most importantly, I would like to rather factor from 6 times 4 times 2. Okay, that 6 is the same as saying, okay, 3 times 2, and then that 4 is 2 times 2, and that 2 is a 2 times 1. All right. So actually, that two, let me highlight them actually. That'll be better if I highlight them. These two, and this 2. Let me write that as a 2 cubed. And then that's going to be a 3 times 2 times 1. All right. And well, that's also the same for this 5 squared times 2 squared times 2 times 1. And then this is simply 5 times 2 times simply as simply a 1, an invisible 1, which could be the 1 factorial. All right. Okay. So with that being said, I'm going to replace, okay, I'm going to go and write y equals to c sub 0, 1 plus sigma n equals 1 to infinity of number 1. What do we have? We have that negative 1, a negative 1 to the n for the alternating factor. And then notice the increasing product, 7 times 9 times 11. So 7 times 9 times 11. dot dot dot. Well, in this case, well, notice how these factors differ by 2 units each. So I'm gonna have a 2n, okay, and then we'll figure out what to add next. Maybe a plus, maybe a minus, we'll see. All right, in the denominator, what do we have? This 5 to the n, this 2 to the n, and 3 times 2 times 1, that's an n factorial, all right? And then the powers, notice how this, let me write it down here, 5 cubed times 2 cubed times 3 times 2 times 1. This guy right here, this 3 times 2 times 1, this 2 times 1, this invisible 1, that's an invisible 1 factorial. This is a 2 times 1, which is a 2 factorial. This is a 3 times 2 times 1, which is a 3 factorial. But you see how this 3, or rather the exponent of x, the power of x, is twice the factorial over here. 4 is also twice the factorial over here. 2 is also the factorial, twice of the factorial of 1. Okay, so that's actually going to indicate that we're going to have a power x to the 2n. All right. So now for n equals to 1, okay, so 2 times 1 equals to 2 plus what number equals to 7? That's going to be plus 5. All right. And this is our final answer. In this case, unlike the previous example, there is no way to write it in terms of factorials to start at our series at 1, because if we try to complete the factorial in the numerator, we may end up messing up the products in the denominator. All right, so in this case, it's not really going to work. All right, so that's a final answer.